Okay, welcome everyone. This is our week 3. Can you believe that? We're almost halfway of our 6-week semester. But first, I have a great news for you guys. We have our first guest lecture confirmed, which means next week you're going to have an extra credit opportunity. Okay, so that will be yay! Yay! So that will be next. Oh, where are you? Sorry, I accidentally touched my screen. Okay, so that will be next Tuesday, same time. Okay, next Tuesday, 6 p.m. in the evening, same link. Later, I will send a message to everyone, to the class. Okay, so our guest speaker is our beloved Professor Bill Selby. So he's very, well, he knows everything about our atmosphere, I would say. And so enthusiastic about the atmosphere and the earth in general, especially for climate change, swell weather, all these very interesting things. So the topic he proposed actually is, Jane, I know they are very nervous when they in the class. They're afraid to ask you because you are the professor. About some questions, right? So the topic he proposed is, well, something you want to know about weather and climate change, but you're afraid to ask. Okay, sounds interesting, right?
Yes.
So everyone, propose your questions. Okay, I will count it and I will give you extra credit. Extra credit. Yes. Okay. So basically, let me make long story short. Okay, your requirement is to, based on Professor Selby's lecture. Okay, to write a summary. Okay, like you write a summary for every module. Okay, what you learned from his speak. But if you ask questions, one question equals to 2 points. How about that? Okay, so you will have extra credit by asking questions. Okay. All right. So later I will send more detailed instructions to our class. Okay. Any questions? Okay. All right. So another thing is I graded your quiz number 2 already, and I released the answer already. So double check the question you get wrong. Okay, I see some common questions, some common problems is number 1, when we talk about the greenhouse effect, okay, how the atmosphere and the ground exchange the energy, the ways they make the balance between the incoming energy and the outgoing energy. Many of you say, oh, the sun shining down, right? And they reflect our earth, and the cloud reflect or scatter away part of it, right? And then when the ground absorb it, actually ground turn the solar energy to long wave energy already. Okay, so it's not right to see the rest of the solar energy is absorbed by atmosphere, because greenhouse gases, atmosphere cannot absorb shortwave energy efficiently. More efficiently, that is a long wave radiation from the ground, from the Earth's surface. Okay, so that is a common question I see. And some of you actually misunderstood the last question. Some of you got the question like this. Greenhouse effect, right? How it works. Some of you say, oh, greenhouse effect help the earth maintain a livable environment, and otherwise will be negative 18 degrees Celsius cold. Actually, if you think what you put the answer there, your answer actually answer another question, which is why greenhouse effect is important, right? Help us maintain a livable environment, right? That's how important it is. But the question asks how it works. So basically ask you to describe the energy flow, the sun shining down, the earth absorb it and emit long wave energy, and long wave radiation energy get absorbed by those greenhouse gases and then radiate back to the ground. Okay, so this is how greenhouse effect works. Okay, you will describe the process instead of how important it is. Okay, but don't worry, don't worry, just one quiz, just one questions. Okay, just a few points. I think maximum is just 10. But next week you will definitely get that back through our extra credit. Okay. All right. So, any other further concerns and questions about the last module? No? Yeah, I haven't finished grading your discussion board yet, but I'm so looking forward to do that this afternoon, my Beijing time, to see your questions. Okay? Yes. All right. Okay. So let's get started about our module 3. Okay. Let me share the screen with you. Right here. Share the screen right here. Share. Okay, so I published the week 3. This week we are going to understand the air pressure and the wind. Okay, and the wind. Okay, so you have the same thing. First, go through the lecture slides. Okay, we'll put our video, this recorded video, on the side. Okay, and you have the study guide, which have a lot of videos I grabbed from YouTube. I think they're very helpful and informative. Okay, and discussion and quiz. Okay, and quiz. So this quiz we'll do next Wednesday. So take your time. Okay, I want to emphasize that you want to study all the questions. You want to be answer all the questions, be able to answer all the questions. I put it here. I think in total you will have 12 or 13 questions in this study guide, okay? And then you go to the quiz. I see many of you take the quiz immediately after, our Tuesday's meeting. Well, I will say don't rush, okay? Don't rush. Make sure you can answer all these questions, then you are ready. Then you are ready, okay? All right. And another thing I want to remind you guys, this chapter, let me share my slides, okay? This lecture, this module actually covers 3 chapters, a lot, okay? And to be honest, I feel a little bit difficult to understand our textbook because they put in such a way, it's written, those 3 chapters is not that good written, okay? And it's a little bit, too many jargons over there and too many foreign words over there, okay? And they could, put it in a simpler way. So that's what I do. That's my job, okay? To grab those informations, to rephrase it in a simpler way for you to understand. Okay, so it's very important to go through our slides to watch this video. Make sure you do that. Okay, and also you don't have to read every single page. Like here, I feel difficult to put the page numbers here actually because I don't like those pages. Okay, and here is a study strategy for this chapter, for this module. Okay, you can see I highlight the key words here. Okay, first, air pressure. Okay, second, surface map and upper level charts, and so on and so forth, right? And then when you go to the, if you want to read the textbook, do a single search, okay, with those keywords, okay? And then you will find the block, the text block to, to explain these key concepts, okay? On our study guide, not study guide, sorry, that is our class module, okay? The second one, you will have this learning resources, okay? And here you have your dictionary. So let me annotate, draw a box right here, Okay, glossary of meteorology. Okay, if anything is not clear to you, okay, go here, do your search. Okay, another way is to watch the YouTube video. But if you feel my YouTube video is not that helpful, not clear, you can use those keywords to do your own search. Okay, to learn more. This is how you study in a more efficient way. Because I totally understand in a normal semester, fall semester or spring semester, this class will last 16 weeks. 16 weeks, and we want to compress it into 6 weeks, which means we have to do a lot of work, right, every week. So definitely keep me posted if you have any questions. Okay, don't stuck there. Okay, it's not the efficient way to learn. Okay. All right, so this is how you study this chapter, okay? All right, okay, so let's get started. Let's get started, okay? And for each key questions, let me bring one more thing. For each keywords, for example, air pressure, okay? You just need to make it clear about those questions, okay? There's a lot of things you could say about air pressure, but focus on understand what's that. You know that already from our lecture, the first module, right? And factors that influence air pressure. What can give you high pressure? What can give you low pressure, right? And how to measure it, how to measure the devices, the instruments that used to measure the air pressure. Okay, focus on those small questions. I put it under each larger topic. Is that clear how to study? Okay, good, thank you. Okay, so let's get started. Okay, so first, air pressure, okay? From module 1, right? From module 1, you know air pressure already. So why we have air pressure? We have 2 reasons, right? Okay, one is, let me annotate, air have the weight, right? Air have the weight. Pressure basically is a force per unit area. For example, every square inch, how much forces you put it on that square inch, that is your pressure. Okay, so if you have some weight, like my mug, right, my bottle, have the weight, I put it on my computer, on my desk, it will exert a pressure to my desk, right? Okay, so the number 1 reason is the air have the weight. Actually, if you are standing here, you can see this is you, this is Jane. Okay, even it's invisible, on top of Jane, on top of your head, actually you have a huge column of air, right? All the way to exosphere, all the way to the top of the upper atmosphere, right? From module 1, you know how tall it is. It's 50 or 500,000 meters or something. It's a huge number, right? That air column give us the pressure, okay? But in addition to that, air molecule also can move, even we cannot see it, okay? Air molecules can, constantly moving, especially when you have the wind, right? So when you, for example, you're in the middle of the desert, there's a huge, strong wind. You will feel those air molecules actually push the sand striking on your face. It's hurt, right? Okay, air molecules, they can move, they can strike onto the surface. So if I strike onto my face, right, I hit myself, I will give myself a pressure, right? Okay, so that's why you can do this fun experiment. You have a cup of water, fill that with water, and you put, cardboard or something on top of it, and you flipped it. You remove your hand, you don't hold it, okay? This cardboard won't fall, because our air molecules, they're striking on this surface, upward, even upward, okay? Help you hold this cardboard, Okay, so from these slides, you want to know two things. We have air pressure is a force per unit area, okay? And why? Because they have the weight. Then they can move, okay? So air pressure, that is on every surface in all directions, okay? Is that clear? Okay, all right, okay. Hold this background knowledge because next slide we're going to study when you have high, when you have low, okay? So, well, let's stay here for a second, okay? So, you know, air have the weight, so we have air pressure. So what would you say? In which cases you have a higher pressure? Weight, that will be when I gain weight, right? If the air is heavy, then Jing is standing here. If on top of Jing, the air is heavy, right? It's very dense. It's very dense. It's like a rock, you know, on top of Jing. Then that gives Jing a lot of pressure, right? But if on top of you, the air is fluffy, very light, you will have, you know, low density, then low pressure, right? So that is why when you climb up the mountains, you know, you need to carry oxygen bottle. You feel the air gets thinner and thinner because, you know, when you're up here, you don't have a lot of air on top of you, right? Because you actually, a lot of air beneath you. They won't give you the pressure if we just consider weight, right? Okay, so that's the thing. Denser air, heavier air will give you more pressure, okay? Another thing, another situation, let's stay here for a second. Air can move. So if Jing is standing here, okay, all the air, for whatever reason, they're striking on Jing. They are descending. They're sinking. They press Jing. Jing doesn't just have a rock. That rock just moving down to Jing's head. Jing will be pressed like this, right? You will have a higher pressure, right? So whenever you see the air is moving to you, you probably will have a higher pressure, right? Make sense? Yes? Okay, so two reasons, keep in mind, okay? Here, all right, let's go to the next slide, okay? So if you understand that, this actually very easy, okay? So factors that affect the air pressure. Number one is our temperature, okay? We're talking about cold versus warm, okay? Here, cold air is denser. Cold air is denser. So cold air is heavier, like I put it here, okay? Remember from the first slide, heavier air give you higher pressure, right? So cold air, if you're standing at the Earth's surface, here, we'll just talk about the Earth's surface, okay? You are standing here. Because the air is denser, you will have heavier air on top of you. So you will have a high pressure. Well, flip side, warm air is fluffy. You know how the air balloon, right? It's fluffy. They expand it all the way to the top. So you will have less dense air. You will have a low pressure on top of you. Make sense? Okay, at the Earth surface. Okay, it's different upper level at the Earth surface. Okay, let me emphasize that. At the Earth's surface. Okay, and movement. The second one is your movement. Okay, your movement. So that is sinking air versus rising air. Okay, like I show you here, you can see, well, here I have a sinking air, right? Jing is standing here, Jing feel a lot of pressure, okay? And you know, Gioni, you're standing here. Sorry, you're more pretty than this one. You're prettier. but the air is rising in your region. So you can see, then Gioni will feel less pressure, right? Because they're not striking to you, it's striking to Jing, right? So you can see here at the ground again, at the ground, sinking air towards the ground, you will have a high pressure, okay? Rising air moving away from the ground, you will have a low pressure, okay? Jargon. This due to the movement, we call that dynamic high. This due to the movement, we call that dynamic low. Those two is because of your temperature difference. We call that thermal high or thermal low. Okay, so that's jargon. Thermal means temperature. Okay. Okay, so here, any questions? Are we good? Yes. Okay. All right. So air pressure should be compared at the same elevation. Always. Always. So you can see on this slide, we just talk about the ground at the Earth's surface. Okay. We're not, compare the air pressure here and upper level, because 100% sure when you go up, air pressure always decreasing. Okay, always decreasing, which means it's not fair to compare them, right? Air pressure is always decreasing as you go up. This is the, the rule, must. Okay, it's a must, because when you go up, the density fast decrease. Okay, so same level. Are we good? Yes. Okay, so now take home message: cold air, high pressure; warm air, low pressure; sinking air, high pressure; rising air, low pressure. Okay, all right. Okay, two more. Elevation, right? Elevation, easy. High altitude, low pressure, because as you go, you have thinner and thinner air, right? Okay, low altitude, not latitude, altitude, low elevation, you will have a high pressure because you have more air on top of you. That's easy, okay? But this one is a little bit confusing. Okay, oh, I notate. This one, moisture, okay? Like I put here, it's counterintuitive actually. Okay, so moist air have lower pressure. Yeah, Burr, like what? Right? I totally feel for you, feel the same way. Well, the air is moist. Like today, my hometown, it's so humid. It's like 70% humidity. Next week, we're going to learn humidity. Okay, it's the air feel very sticky. And this morning when I swam, I feel I couldn't breathe. The air is too heavy for me. Okay, but no, actually. Moist air corresponds with low pressure. I feel it's hard to breathe actually just because you have a low pressure. Because outside the pressure is low, it's hard to pump in the air into my lung, right? I need to work hard, like deep breath, right? To pump the air in. But if the high pressure, they can just automatically pump into my nose, into my lung, right? I don't have to do that much work. Okay, so moist air have a lower pressure. Dry air actually have a higher pressure. Okay, why? Well, here you have a video to explain it. But long story short is this. It's due to the weight of your water molecules. Okay, dry air, moist air. The difference is, well, it's like no common sense. Moist air, you have more water molecules. Okay, but the fact is, the thing is, our air is just like a jar. Okay, this jar can only hold certain number of molecules. Doesn't matter what kind of molecules, okay? Can be nitrogen, oxygen, argon, carbon dioxide, or other things, okay? But certain amount, like let's say 1,000, okay? Okay, 1,000 molecules in total, okay? In a dry air, okay, you don't have that much, water molecules. That's fine, okay? This one also have the 1,000, the capacity, okay? Well, then you have the moist air. You need to bring more water molecules in, right? Well, the maximum molecule your jar can hold, let's say just 1,000. In order to bring those water molecules in, you have to kick out those nitrogen molecules or oxygen molecules or other molecules. Okay? Total, our room can only hold 1,000. Okay? Now it's full, but you want to bring more people in. You have to kick someone out. Right? So the thing is, our water is light. The molecular weight of water is 18. Okay, it's 18. But our nitrogen is 24. Okay, our oxygen is 32. Okay, carbon dioxide is 44. Okay, so you can see water is a lighter one, is a lighter molecule. So when you replace those heavier molecule with lighter molecule, the weight of your air actually become lighter. Okay, so that's why we know lighter air, you have less pressure, right? So that is why moist air have low pressure. Make sense? Yes, when I first studied, I'm like, what? No way. Okay, so you can see here, okay, that's the reason. And this video give you more information, okay? And very fun, it's a fun video. Okay, clear the drawings. Okay, now you know, high elevation, low pressure. Low elevation, high pressure. Moist air, low pressure, remember that. And dry air, it's a higher pressure, okay? All right, then measurement. Remember, for the air pressure, we want to understand 3 questions. Number 1, what's that? Number 2, factors that can affect air pressure, then how to measure it, right? How to measure it. So here, the instrument, you want to know the term, it's called barometer. So that's why BAR is a unit for your air pressure. It's bar, okay? And on the map, we call that isobars. Isobars, that is the line you see on our map. You will see that on the next slide, okay? But in addition to bar, okay, this unit, you have other unit to measure atmosphere. It's just like you measure the length, you measure distance, you can use miles, right? You can also use kilometers, right? Okay, you can also use meters, you can use inches. You have many, many units. It's just different unit, okay? So let me explain what's that. ATM represent standard atmosphere pressure, okay? Standard atmosphere pressure. That is measured at the sea level, okay? With the degree, I think it's 15 degrees Celsius, okay? Our average Earth's temperature, okay? It's 1 standard atmosphere pressure. It's just a unit, okay? And then this one is millimeter mercury, okay? So why is that? Actually, that is a very fun experiment, okay? So for example, here, oh, my computer freeze. Let me end it, okay? Come on. Okay, let's see. Okay, I think it's good. Let me turn out the back. Okay, so it's right here. Okay, so it's this experiment. Okay, let me describe it. You have this dish. Okay, in a dish you have, you know, liquid mercury. Mercury is a metal, but it's liquid. Okay, it's weird, right? And then you put a tube. One end is sealed. One end is sealed, and this tube is vacuum. Nothing in it. Okay, no air, no molecules in it. Okay, and then you put this tube upside down, put it in your dish. You will see, oh, the liquid mercury slowly goes up. Okay, rise up in this tube, and the maximum height they can go. Okay, the maximum height. Where's my mouse? Okay, here we go. Okay, the maximum height they can go from the top to the surface of this mercury dish, the liquid level, that is a 76 centimeter, which is 760 millimeter. Okay, so that is this height that measure the standard atmosphere pressure at the sea level, at the ground. Okay, so that is why we have that. This actually is invented by 3 meteorologists, okay, and physicians, scientists study physics, okay, physicists, okay. I have hard time to pronounce their name because they're from Italian, okay. But watch this video, okay. You will see how smart and how those 3 scientists, they always think out of box to design the instruments to measure the air pressure, okay. But that's millimeter mercury, okay. And another one is hectopascal. Okay, there's actually the name of one of the scientists, Pascal, okay, to measure the air pressure. And also millibars. See, bar is a very large unit, okay? So usually we will use millibar, okay, millibar to measure the air pressure, okay, at the sea level on average, okay, is this number, okay? And this is the fun one, guys. This is the fun one. PSI represent pound per square inch. Pound per square inch, which means you have a square inch, right? You put this, you know, like a quarter. You put this quarter at the surface, Earth surface, okay, sea level, and the pressure on that quarter will be 14.7 pound. That's a lot, right? That actually is a lot weight. So you will feel, oh, that's a pressure. That's a pressure. Okay. And I want you to keep in mind this number. Mean sea level air pressure, global average, is 1013.25 millibar. Okay. We use millibar a lot in the rest of the modules, okay? And you want to memorize this number, okay? Mean sea level air pressure, 1013.25, okay? All right, so from this slide, we know the instrument you can use to measure air pressure is called barometer, okay? It's like this, a barometer, okay? And unit, you have various units, standard air pressure, standard atmosphere pressure at the sea level, 15 degrees Celsius, okay? Millimeter mercury from this, you know, experiment, and hectopascal, millibar, pound per square inch, okay? So you know that's just different unit for you to measure the air pressure, okay? Okay, make sure you watch this fun video to see how they invent barometer. Okay. All right, so far so good. Not that heavy, right? But when you read the textbook, you will give up already, I think. I gave up already at this point. Okay, all right, enjoy, okay? All right, then surface air maps. Surface air maps, okay? So first of all, where to see today's map? Here, Click on this link. And you can see here we have this. Let me zoom in a little bit. Okay, maps showing present situation. Okay, and you can see this surface maps with isobars. Oh my gosh, I know what isobar is, right? I know bars, that is the thing, the unit to measure the pressure, right? So what is isobars? Isobars, iso means equal, okay? Means on those lines, you have equal air pressure. Let's take a look at it about today's situation. So let's see. Let's go to this one. North America, isobars only, because I don't want to see a busy map. You know, that's, you know, scare me. Okay. So let's go to North America. Okay, let's continue. Okay, here we go. That is July the 8th. Oh, that is from my time zone? No, that's actually is the UK, the prime meridian, time zone number 0. Okay, time zone number 0, that time. But we are July the 7th, right? Okay, so let's zoom in a little bit, make it larger. So you can see those are the isobars, guys. Let me annotate. Do you see those lines? I'm doing my best to redraw it. Do you see those lines? Those are the isobars, okay? Isobars, like I mentioned earlier, they pass the location with equal air pressure. So you can see here, at this location, it's 1,008 millibar, okay? Up here in Canada, same thing. Let me erase this part. Eraser. Okay, so you can see here, it's also 1,008 millibar, right? Let's go to home. Well, California, Southern California. Here you can see, oh, this line is also 1,008, right? But if you go to San Francisco or Northern California, right here, maybe that is Mountain Shasta, okay? Well, you will see this line that connect all the locations with the air pressure 10, 12 millibar. Okay, so this is how you read. So for example, let me give you a question. Okay, so for example, in Texas, right here, what's the air pressure?
10, 12.
10, 12. 10. High five. You got it. Yes. Okay, so Gioni, right here, I think it's in where it is. Lake. Let me see the lake.
Yeah. Lake Michigan.
Yes, the same thing, right?
Yeah.
Great. How about New York here?
1016.
Yes, you got it. Okay, but how about here? Sorry, let me try to draw that here. For example, here, Lake Michigan, south tip of Lake Michigan. How about here?
Ten, 12.
10 what?
10, 12.
10, 12. Well, 10, 12 is here. If it's 10, 12, the line should pass this location.
So the line is showing like it's going increasing. So probably it's like 10, 14, probably, or.
High five, Burr. You're an expert. Yes, exactly. If you don't see the line, but you see their neighbors, right? One line on to the one side is 10, 12, and another one is 10, 16. Then it's in between, it's also increase in this way, right? So in the middle, maybe I will say it's like 1013 or 1014, like that. Does that make sense, guys?
Yes.
Yes? Okay. How about here? Minneapolis, Minnesota. And this is, should be Montana? No, North. This is North Dakota. Okay, how about here?
10-9.
10-9, yes.
9. But
What?
the line to the left is 10-8 as
Right.
well.
10 to the line to the left is 10-8. The line to the right is 10-12. So what do you say?
I say 10-9, but I guess why I was confused is because the line to the left of 10-8 is also 10-8. You see, go left.
Go
To the
left.
Yep, left.
Oh, don't worry. We just consider the neighbors.
Okay.
Don't go that far.
Okay. Okay. I was on the right track.
Yes, don't go that far. You just need to find the two boundaries, okay? The two boundaries next to you, the lines, and then try to estimate. Use those two numbers.
Okay.
Okay? Yes.
But what if I was in the middle of the other two? What if I was in
1/3.
Oh, okay.
Right?
Okay.
Yes.
Yeah.
You just need like a ruler. You just assume a change in a linear way. Okay? Continuously. You don't jump. Okay.
Got it. Thank you.
Okay. And also, guys, you see those big L? Do you see that? Those big L actually represent, you can also see those L, it's circulated with those, isobars, right? This actually represent a low pressure center. Okay, sometimes you will see high, you will see high. That means a high pressure center. It's round. Okay, so that is another thing. Okay, I hope you can read it. But keep in mind, guys, this is the sea level. This is the sea level. Okay, but wait, you probably have this question. Jing, I know here, this is Utah, right? And we also have here, this is Colorado right here. We have a lot of mountains here, right? But here we produce the sea level pressure. It's not the city, the station, that pressure I measured in, in Colorado, because they're mountains. It's not at a sea level, right? So how do you produce this map? Okay, let me show you. Okay, let's go to my slides. Okay, let me clear my drawings. Okay, here we go. Okay, so let me emphasize, on this map, what do you want to know? Okay, you want to know what is isobars. Okay, you want to know high, like I think on Sunday, I download this one. Okay, you can see the situation changes, right? That's every second they change. Okay, and high, low numbers on the isobars represent the air pressure at that location on that line. Okay, but if you don't have the line, you need to estimate. Okay, and here's another thing, isobar spacing. That's can be an experience when you read this map. If you see the isobar is very busy, like here, like in Mexico and Texas, this part, you can see they're very busy, very crowded. That actually means your air pressure change very fast. Later you will see it's called greater pressure gradient, steeper slope. Okay, but if here you don't see them change that much, that means they change very slow. You have a very slow pressure change, which actually will give you the weak wind. But that's later. Okay, so spacing is also very important. Okay. All right, so then let's go back to our question. Okay, how they was produced? Well, you need to recalibrate, recalculate to the higher elevation to see the air pressure you can actually measure at that location. Okay, so this surface map, from certain perspective, actually to a certain degree, it's not that useful for people with higher elevations because it doesn't show you the actual pressure at your location. Okay, it's recalculated to the earth surface, recalibrate to the earth surface, sea level. Okay, so this is how you calculate it. You want to remember this magic number. It's actually not a magic, it's a global average. Okay, you always, air pressure always decrease when you go up, right? For example, when you go to Colorado, when you go to Denver, okay, every 100 meter you go up, your air pressure decrease 10 millibars. 10 millibars. Okay, so for example, you have your city A right here. Let me move our checkbox here. Okay, you have your city A right here, and the elevation is 600 millibar, right? Okay, and the air pressure you measured in your city, okay, you use a barometer to measure that air pressure, and the reading is 952 millibar. Okay, but your higher elevation. Okay, when you try to produce the map at the sea level, you should count it. Okay, you need to add 60 millibar if you want to know the sea level air pressure. Does that make sense? Okay, reverse the same thing. If you have this number, you have that map, right? You have that map, you read the number for Denver. Oh, the sea level pressure is 1012. But Denver's elevation, let's say it's not 600 meter, but let's say pretend it's A, okay? Every 100 meter, you need to decrease 10. So 600, you need to minus 60 from your 1012, and then you get this number. Does that make sense? Okay, so that is a little calculation when you use this the surface maps, okay? But don't worry, I won't ask you to calculate it. You just need to know the concepts, okay? You just need to know the concepts. The surface map, okay, is not showing you the actual air pressure. In the textbook, they call that station measurement. Okay, the station measurement is different. It's different because you need to considerate the elevation. Okay, and the number is 10 millibar per 100 meter. Make sense? Okay, good. Wow, you guys genius. Every time I teach this part, I'm still like, wait, I never do math. I can never do math. Okay, I'm like, okay. Okay. All right, not that scary. Okay, just the plus and minus, right? Okay, but here. All right, then upper level charts. Okay, upper level charts. Let's take it slow, guys, because this one I probably say it's maybe the most confusing one. Okay, the most confusing one, and a lot of people, make mistake on that. Okay, let me find the pad for my mouse because my table cannot detect the signal. Okay, it's right here. Okay, much better. Okay, here we go. All right, so to this point, we just talk about the sea level, right? Then let's talk about the upper level. So when you go up, like 1,000 meter, 3,000 meter, 6,000 meter, how to draw this map, okay? They define in different way, okay? So those upper level charts, we also call them, AKA also known as, okay, constant pressure chart or isobaric chart, jargon, okay, just different names, but it's upper level. For upper level, you measure the air pressure, you map the air pressure, okay? So let's see, you can see here, instead of showing the pressure variations like our, sea level, right? Here, Lake Michigan and, Chicago, they have in the city, they have different pressure. Or in Southern California, we have different pressure, right? Instead of showing the air pressure difference, we show the altitude, we show elevation. Okay, so I want you to use this chart to understand this, so-called constant pressure chart or isobaric chart. They show you the elevation. Elevation of what? To which elevation you can find certain pressure. Okay, to find certain pressure. So for example, here, let's use this 500, this one. Okay, this average, on average, you have to go up to 5,600 meters above the sea level to find 500 millibar. That air pressure, the same air pressure, okay? Feet, 18,000 feet. So which means on this, the grade surface, on this surface, everywhere you have equal air pressure, which is 500 millibar. Does that make sense? So basically means to which elevation, they show you the elevation, the variation you see here, higher height, lower height, right? They show you have to go up to which elevation you can find a constant air pressure, in this case 500 millibar. Make sense? Okay, so to which elevation you can find your target air pressure. Okay, so here's the thing, you can see this is to the south, like Mexico, like Baja is hot, right? Mexico at this point is hot. From previous slide, the hot air there rises, they expand, right? Okay, they expand. Well, when you go up right here, you always have decreasing pressure, but as the air expands, the pressure decreasing is slower compared to the northern part. The air is heavy, right? Because those warm air, they expand, the air moving into that area, right? You have thinner and thinner air, but ground level, the air moving in will make it up, will make up the loss of the air molecules. They're moving in, they give you higher pressure. Even, they make up the decreasing of the air pressure, right? So which means, long story short, over a very hot surface, because the air is rising, okay, the pressure decreasing is slower, okay, as you go up. It's always, decreasing, but over the warm surface, the rate, the speed is slower compared to the cold air, because cold air, usually they're sinking, they're descending. Okay, so which means over the warm surface, you have to go a little bit higher to find 500 millibar, your target millibar. Okay, and if you above a very cold surface, like now Canada or Antarctica, okay, the northern part of the country is very cold, then the air is dense. You don't have to rise that far that high to find your target air pressure. So that will give you a low height. Make sense, guys? Okay, so usually on average, okay, you always see, for example, this part is, you know, San Diego, SD. Okay, and this part, let's say, that is Seattle. Okay, let's just use S. Okay, or Seattle, or let's use Canada, C. Okay, clear. Okay. Oh, I know a good way. Okay, let's see, Toronto. Okay, hope I spelled that right. Okay, San Diego and Toronto. Okay, one is the southern, to the south, right? One is to the north, and San Diego is much hotter than Toronto, right? In Canada. Okay, it's cold up there. And then usually you will see the isobaric chart to the south, you have a higher height. Okay, because the ground is warm, the air expanding. Okay, and over the Toronto, you will see that 500 millibar or any of these millibars, the elevation is lower. So basically their atmosphere is compressed. It's very, you know, dense, you know, close to the Earth's surface. But over the warm area, expand a lot. Okay, expand a lot. Make sense? Okay, so let's take a look at one real example. So go here. Oh, actually not here. It's this. Okay, the same website. Okay, and then you will see surface. No, I want to see upper level. Sorry, maybe that's a later the slide. Okay, let me use another one. Let's see. It's not this one. Okay, it's this one. Let's just do this one. Okay, this actually from our textbook. Okay, you can see here. Okay, so you can see same thing. Clear the drawings. Okay, you can see this is the south. S represents south. Right here. Okay, and N represent north. Okay, normally, typically, to the south, this constant millibar is the constant chart is always higher to the south. Okay, and is always lower to the north, which you see here. This actually is an example. Okay, so you can see those lines, actually we call that contour lines right here. Lines connecting equal elevation. Okay, so you can see those numbers to the south in Mexico is always higher than the number to the north. Okay, this 5,400 and this one is 5,700 meters above the sea level. It's always like that because to the south it's warmer. Make sense? Okay, then guys, want your attention. This is very important and could be confusing. So you see high and low here, right? Okay, previously when we read the sea level, we know high represent high pressure, low represent low pressure, right? But not here. Since we represent the elevation, not pressure, this means high elevation. You have a high mountains here in terms of pressure. And here you have a low elevation. You basically have this depression in terms of elevation. So over here in Canada, you don't have to rise that high to find 500 millibar. Make sense? Okay, again, it's the elevation, it's not pressure, okay? On this map, actually, everywhere pressure, they're same. They're 500. Okay, they're 500. Okay, and in addition to that, sometimes we also have, you know, the temperature plotted, this temperature, okay, degrees Celsius, I think, okay, that's different. That's another, information you can get. Yes, Burr, question.
Professor, so what is the real life situation that we use these constant charts for? Like, when are we supposed to use this chart? Like on a daily basis or something?
They remember later you will see upper level airflow. You can see those arrows represent upper level, how the airflow. We call that geostrophic wind. This can have the very close connection to your ground. Okay, if you see the upper level diverging, moving away from your area, highly likely at the ground you will have a low pressure, and low pressure always give you stormy weather. Yes, exactly. Yes, that's scary, right? Okay, so that is why. But great question. Upper level, ground, they're connected. Okay, all right. Okay, so well, ask me questions whenever you have. Okay, all right. Okay, then let's take a look at it. This is actually the fun part. Okay, our upper level charts. Let me use a metaphor. It's just like a roller coaster on pier, right? It's like a roller coaster. Okay, have you enjoyed one ride on your roller coaster? Do you have the experience? When you go up, the train actually is very slow, right? The train is very slow. And then later, woo, push, right? When you go down, you actually move very, very fast. It's very scary, like that, right? So when you go up, you go slow, but when you go down, you go fast. Same thing here, upper level airflow or wind. Okay, let me show you. Now you know this is the upper level charts. Okay, upper level charts. And you can see here, we have a high, means here we have a high mountains. So basically our air from this end, okay, they move up, right? They actually go up, climb your mountains. You have a high here, high elevation. Remember, high means high elevation. Okay, it's a ridge, it's a mountain. You go up here and then you go down, right? Okay, that means those wind, they are slow. Okay, where is my? Okay, let's see. Oh, I need to do this way. Okay, this is your ridge. This is your ridge, means it's a mountain top. Okay, so when your air climb up this mountain, they go slow. This is the trough, means it's a valley. Okay, so you can see your air go here, they rise up, they descending, and then they rise up again. Okay, it's like this bumpy surface. Okay, this called trough, this called ridge. But you can see here, when they climb the mountains, they slow. Why? How can I tell that? These actually are wind bars. Okay, the symbols, you represent wind. So you can see, you can look it up. It's like a little flag, right? Let's look it up here. It's what? Let's see. It's oh, need to draw here. 55 to 60 miles per hour, or you use the standard unit is knots. Okay, it's 48 to 52 knots. That's a little bit less than 1 mile per hour, right? Okay, but you can see the airflow descending, like you descending around roller coaster, right? You can see those are small flags and 2 bars, right? Small flags, 2 bars, one is long, one is short. Here, 70 something miles per hour. It's faster, right? And then when they pass this trough, this depression, they rise again. So you can see they become slower again, right? Because they have to climb up another mountains, right? Okay, so this is how useful this upper level chart is. Okay, so by the way, this is a wind barb. Okay, you're going to use it to, you can calculate the wind, the speed. Okay, the flag means 50 knots. Okay, the bar means smaller one means 5. Okay, and smaller one, this little bar means 5 knots. The long one means 10 knots, and then you just add them up. Okay, but that's another story. When we study the weathers, I will lead you to read to calculate those wind speed. Okay, so if you want to see a more detailed explanation, go here. Right, go here. Okay, make sense? Yes, Burr.
Professor, so I heard you saying about the mountains might have effect on the wind speed, right?
Yeah.
So in the open water, even the speed of the wind is different, right? Before we hit the mountains.
Exactly. Very great questions. Why? Because why you say over the water, you have different speed?
Yeah, because I do sail, and it's sometimes going one side is very fast. When I come back, it's very slow.
Exactly. For example, you have very smooth lake, very peaceful lake, right? Compared to a lake with choppy waves, very rough, right? They have different speed. That is another thing. The forces on wind, you have more friction on the choppy waves. That will slow down your wind, actually. Yes. Okay, that's later, but very great question. You're a sailor. I didn't know that. I admire you.
Thanks.
That's another skill I want to learn, actually. I want to sail. I want to surf. I can swim in the ocean now. Okay, so very good. Burr's question actually is a very good trailer for our next section. Okay, forces on wind. Okay, so first you want to know what is wind. That is a horizontal movement of your air molecules. Okay, and what causes wind? Well, pressure difference. Okay, certain part you have a high pressure, you have dense air, right? Certain part you have low pressure, you have less dense air. So naturally they want to balance out. So you will have this movement of the air molecules give you the wind. Okay, pressure difference. But keep in mind, air is always flow from high pressure to low pressure. Okay, so let's watch this video. Okay, I know you're tired. Let's take a break, okay, to see how the pressure difference can cause wind. Okay, let's watch this video. Hold on, let me see. I need to stop share, otherwise you will have very low volume, okay? And then let me redo that. Here, share with computer sound. Okay, here we go.
Welcome to Fun Science Demos. There's a lot going on here, but you can't see it because what we're going to take a closer look at today is air and how air moves. And we're going to use this setup to give you a better idea of how wind works. So our setup's pretty simple. I have a container of soil that I'm heating up with these hot lights. I have a container of ice water, and I have a nice clear tube connecting the two. And believe it or not, the air is moving between these two containers. I just can't see it because I can't see the air. Now to help us see the air, we're going to use this really neat smoke stick that's going to generate some very safe and harmless smoke to let us see what's happening in the air. So let's jump in to see if we can figure out how wind works. Now, through science, we've discovered that things heat up at different rates. What does that mean? And as the land heats up, it heats up the air above it. And through science, we've discovered that when air heats up, it spreads out, it expands, and it becomes lighter. And because it becomes lighter, it rises. So you can't see it, but I have all of this air that's being heated up and rising. Now, take a look over here. The water's cold, and through science we've discovered that when air gets colder, it gets denser, it gets heavier, it compresses, and that means it sinks. So I have sinking cold air over here, I have rising warm air over here, and as that warm air rises, this sinking cold air sweeps in and takes the spot of the rising warm air. So we actually have wind happening through this tube, but we can't see it. Enter our smoke stick. So now we're going to introduce some smoke and see if we can watch how the air moves. So here we go. Bring my smoke stick in, get this thing charged up, and I'm going to put it here. And you should be able to see, yeah, I actually have a small current of wind moving through my tube. You can see the smoke. Just follow the wind current through the tube, and as it comes out over here, it's rising. That is how wind works. Now you might be thinking I was shooting the smoke through this tube and that's what was making it move. So I'm going to reverse it. We're going to try shooting the smoke in this way and see which way the wind's blowing. So here we go. Let's charge up our smoke stick, get it fired up. I'm going to come in here and try and shoot it. You're going to see I can't get it to go through the tube, because the air is moving through the tube this direction and it's pushing it out. Even if I try shooting it in the tube, I'm going against the wind and it's not working. So remember what's happening. The warm air is rising, it's lighter. The cold air is sinking and it's sweeping in to take the spot of the rising warm air. And the wind current is going this way. So let's see this one more time. Warm air rises, cold air sinks, it sweeps in and takes the spot of the rising warm air, and we have wind. And look at it move. So think about what we've just shown you. We've shown you that when we heat things unevenly, that's what makes the air move. Think about that as our planet. Our planet has different areas being heated unevenly. The sun's really hot around the equator and it's really cold around the poles. Well, that uneven heating of the Earth makes the air move. But also think about this. Our planet is spinning, and that spinning also helps make the air move. So really two things are responsible for wind: the uneven heating and cooling of the Earth, and the spinning of the Earth all helps make that air move. And even when we can't see it, that air is moving all around us. One more time. We have wind. If you want to learn more about wind or weather, check out our links in the video description. Science is so cool, even when we can't see it. Thanks for watching.
Okay. Does that make sense, guys? Yes? Give me some feedback.
That was awesome.
That is awesome. Thank you, Ian. I hope that makes sense, okay? So I will say this is the best video I found for this chapter to help you visualize the wind and to see how the pressure difference, can help you make the wind, okay? But like the professor, he mentioned in the video, pressure difference, number one reason, right? But also the earth spinning also help the wind move. And Burr shared with us his experience when he sailed on the sea. Well, different, surface, you also have different wind speed, right? Okay, that is the forces, 3 forces on your surface wind, the wind we can feel, okay? So here, 3 things: pressure, gradient, force. Okay, let me annotate it. Oh, I didn't share, sorry. Okay, so it's this one. Okay. Yeah, a lot more sense, exactly. Okay. All right, so do you see my computer? The screen? Yes, good. Okay, so here, number one, that is pressure gradient force. That is pressure difference. Like mentioned in the video, equator is always hot, right? North Pole, South Pole, always cold. We constantly have this uneven heating from the temperature chapter. You also know this, right? Okay, different area, you have different temperature. That's why you have the wind, okay? But in addition to this pressure difference, we also have one force is due to the Earth's spinning. We call that Coriolis force, okay? And another, the third one, to the surface wind only, is your friction, because the Earth is rough, right? The Earth is rough. You have, you know, houses like downtown LA, right? You have those high skyscrapers. You have the, you know, trees. You have many, construction site, for example, in LA, that make the surface very, very rough, right? Compared to, you know, Antarctica, the surface is ice. You can ski, right? It's very smooth. So they have different friction and you have different wind speed, right? Okay, so that is the three forces you want to consider, okay? All right, clear my drawings. Okay, let's go to the next one, okay? So pressure gradient force is like this. Okay, pressure gradient force. Pressure gradient basically is the change in pressure over a given distance. So you can see, let me annotate A and B should be here, okay? Or 1 and 2, those different locations. You can see you have different density, air density, you have different pressure, right? Over A, close to 1, this location, you have a higher pressure. You can see it's higher, right? Down here, that is lower. You have pressure difference. Think about it. Think about it. You have this, you know, a slope, okay? A slope of pressure. And to this end, to the left, is higher. To the right is lower, right? You have this slope. And pressure gradient is, well, how much pressure changes as you go from 1 to 2. Okay, so that is the equation. Delta P, that is the pressure difference. And the D is your distance. For example, the pressure change in this case is 16. Right? 16 millibar from 1 to 2. And let's say, you know, this is millibar. It's hard to write. Okay, like this. And your distance is like 1,000 meter. Let's say that. Okay, won't be that fast. Okay, let's say 100 kilometer. Okay, 100 kilometer. So the pressure gradient between A and B, between 1 and 2, that actually is, well, every 100 kilometer pressure changes 16 millibar. That's it. Okay, but let's say you have another distance. Okay, let me erase here. Okay, let's say it's not 100, it's 50. Mouse wings, okay, it's 50 kilometers. So you can see over this shorter distance, you have the same amount of pressure difference, right? You change fast over the distance. So that we call a greater, and this number also become greater, right? Larger, greater pressure gradient, the force, okay? On your map, you will see it's here, okay? So over a shorter distance, you have huge pressure changes. you will see isobars. You can see they're very crowded right here, right? We call that steep pressure gradient. Steep pressure gradient. But over here, you can see the same amount pressure changes, but over longer distance. They change slowly. So we call that gradual pressure gradient, and then that will give you the very weak wind. Okay, so that is the number one force you want to know, pressure gradient force. Okay, pressure gradient force. So because of this force, let me clear my drawings. Okay, because of the, if you just have this one, okay, your wind will be 90 degree to those isobars because this force is 90 degree to isobars. Okay, and narrow spacing, you have steep gradient, you have strong wind. Wide spacing, you have gradual pressure gradient wind, you have slow wind. Okay, so this is how you determine your wind direction and speed just by taking a look at your pressure gradient force. Make sense? Okay, sort of, right? Okay, later let me give you a practice, okay? All right, let me clear that. Okay, so for example, this one. This actually is, this is where? Hurricane, right? This is in New York, okay, in the east coast, to the east coast. You have this low pressure. You will see your isobar. This is surface map, okay? This is the surface map. Those are the isobars, right? Same thing here, you have this high pressure, those are the isobars. So you can see here, high pressure here, low pressure out there. Your pressure gradient force, oh, sorry. Drawing. Your pressure gradient force actually is this way. You can see they perpendicular to your isobars. Okay, on this map, the same thing. Why the wind blow like this? Because they have to go inward first. Okay, they have to go inward first. Here is a high pressure, higher pressure. Here is a lower pressure. Okay, here's a lower pressure. Oh, by the way, the wind means the wind blow this way, okay? The wind blow this way. This is the tail of the wind. Those bars, those flags, this means the wind blow this way. And here the wind blow this way. Okay, they're moving in. They always try to perpendicular 90 degree to your isobars. Okay? All right, okay, so this is one, how you see that on the map. Okay, then the second one is your Coriolis force, okay? Coriolis force. Coriolis force is just because the Earth's spinning, the rotation of the Earth, okay? Well, here's several facts you want to memorize, okay? This is from our textbook, but they just want to tell you some facts, okay? Number one is there's no Coriolis force at the equator, no Coriolis force, okay? Greater when you go to the two poles, okay? When you add the North Pole or South Pole, you have the greatest Coriolis force, okay? And it's also increased with wind speed. So when you go faster, okay, your Coriolis force will be more obvious, stronger, okay? And it's always 90 degree to the wind direction. So for example, your wind, you want to move this way, okay? This force, let me change the color, is always 90 degree. This is 90 degree to your wind direction. It's not your, direction, it's your wind direction. Well, where it is? It depends on which direction, to the left or to the right, right? Northern hemisphere to the right, okay? Southern hemisphere to the left, okay? So this is your Coriolis force. So basically the the effect of your Coriolis force is to change the wind direction. So you can see your wind want to go this way, want to go to the northeast, but Coriolis force will turn that around to go this way. Okay, to go this way. So this is the Coriolis force that change the wind direction. Okay, so I want to share with you another video. Okay, that will make a lot of sense. Okay, so let's watch that. Stop share. Sorry, I need to share with the sound. Do you see the video here? Yes, okay. Coriolis force.
If you've ever watched the news during a hurricane or wintertime nor'easter, you've probably noticed that big storms spin over time as they travel. In the northern hemisphere, they spin counterclockwise. But if you were watching a storm in the southern hemisphere, you'd see it spinning clockwise. Why do storms spin in different directions depending on their location? And why do they spin in the first place? A storm's rotation is due to something called the Coriolis effect, which is a phenomenon that causes fluids like water and air to curve as they travel across or above Earth's surface. Here's the basic idea. Earth is constantly spinning around its axis from west to east. But because Earth is a sphere and wider in the middle, points on the equator are actually spinning faster around the axis than points near the poles. So imagine you were standing in Texas and had a magic paper airplane that could travel hundreds of miles. If you threw your airplane directly northward, you might think it would land straight north, maybe somewhere in Nebraska. But Texas is actually spinning around Earth's axis faster than Nebraska is, because it's closer to the equator. That means that the paper airplane is spinning faster as well, and when you throw it, that spinning momentum is conserved. So if you threw your paper airplane in a straight line toward the north, it would land somewhere to the right of Nebraska, maybe in Delaware. So from your point of view in Texas, the plane would have taken a curved path to the right. The opposite would happen in the southern hemisphere. An object traveling from the equator to the south would get deflected to the left. So what does this have to do with hurricane spinning? Well, at the center of every hurricane is an area of very low pressure. As a result, the high-pressure air surrounding the center, or eye, of a storm is constantly rushing toward the low-pressure void in the middle. But because of the Coriolis effect, the air rushing toward the center is deflected off course. In the northern hemisphere, the volumes of air on all sides of the eye keep getting tugged slightly to the right. The air keeps trying to make its way to the middle and keeps getting deflected, causing the entire system to spin in a counterclockwise direction. In the southern hemisphere, where the Coriolis effect pulls air to the left, the opposite happens. Storms spin around the eye in a clockwise manner.
Okay. Does that make sense, guys? Yes? Sort of? Yep.
I was confused with the paper airplane though, because if the direction of the air is in the northern hemisphere goes counterclockwise?
Yes. Okay, let me share with you this. I think it will make sense. This one. This actually is the next, this slide, okay? So you can see in the video, you learn that in our, at equator, Earth's spinning faster. Why? Because equator is fatter, right? It's longer. But you know when the Earth spinning for the entire circle, that is 1 day. So which means everywhere we just have 24 hours, but we need to finish this spinning, right? So people living at the equator, they have a long distance to go. So they're better spinning faster. right? But at the North Pole or South Pole, it's just 1 point. What do? In one day, you basically just like this, right? Okay, so you don't have to spinning actually. The Earth, just 1 point. You have no distance to go. Okay, so that's why it mentioned when you go to the higher latitude, you can see this speed. Oh, let me annotate it. Okay, right here. This speed actually decrease when you go to the higher latitude, right? Okay, so imagine you have a paper airplane like Gioni's question. Okay, so you want this paper go up to the North Pole, for example. Okay, but because the paper is from a location closer to equator, it's faster. It also carry the momentum go to the right? The Earth spinning this way, like my red arrows go this way, right? So at the beginning, you threw the paper to the north, but our Mother Earth carry the paper to the east. So you have to combine those two effects. That's why it have to be deflect to the right. Make sense?
Makes sense.
Okay, great. Let's practice to the northern hemisphere. You have another paper airplane. You want to throw to the South Pole, but equator spinning faster than South Pole, right? So you have to combine those two, deflect to this way. Okay, so remember that is the wind direction, not your left or your right. So you have to turn around to follow the wind, right? That is to the left. Make sense? Wonderful. Wonderful. Okay, so that is the thing, okay? But just remember in the northern hemisphere, to the right of the wind moving direction. Okay, southern hemisphere to the left of the wind moving direction. Okay. All right. Okay. So here, the last one, forces. The third force, friction. Okay, like Burr shared with us. Clear the drawings. Okay, so when you're close to the Earth's surface, the Earth's surface is rough, you have a higher friction. But when you go up, actually not that high, 3,000 feet. Okay, 3,000 feet, you will free of friction, no friction. Because upper level, the air is smooth and you are very far away from the Earth's surface, right? It's less rough. So the friction will be 0. So jargon, we call that, here, let me change the color. We call that planetary, oh, what's that? Ah, gosh, okay, here we go. Share again. Okay, you see that, right? Okay, good. Annotate here. Jargon is called planetary boundary layer. Okay, basically the layer you have to consider the friction. How thick it is? 3,000 feet. Okay, 1,000 meter. Not that high, actually. Okay, so that is the air. You see friction, you see turbulence, you see eddies, you see those gusty wind. Okay, but up above this level, you don't have that. So that's why our airplane guys, they want to fly very high, right? Because you don't want those turbulence. You should go beyond this planetary boundary layer, friction layer. Okay? All right. Okay, so here. Okay, so then let's consider upper level wind first. Okay, upper level wind, they're usually very high, like our 500 millibar, right? They're 5,000 something meter above the sea level, 18,000 feet. So definitely free of friction, no friction. So those upper level wind, just the two forces on them. one is your pressure gradient force. Okay, like you see here. One is your PGF. Your PGF is always from high pressure to low pressure, right? And the other one is your CF. So you can see because of those two forces, your upper level wind, actually, when they go to the lower pressure, okay, so you can see from 908 to 900, when they go to the lower pressure area, they constantly being turned in northern hemisphere to the right, right? So when I go to the north, I constantly turn to the right. So eventually your wind will be like this. They parallel to those isobars. They parallel to those, contour lines. Okay, they can be turned all the way to this direction. To that point, your CF, Coriolis force, and your PGF, they balance out. Okay, so eventually they can be parallel to your isobars. Okay, there's another fun thing is if you see your isobars is not just those, have equal spacing. You have narrower space over here. It's just like the river, they run into certain tunnel. Okay, they got squeezed, right? They got squeezed. They will run faster actually at those bottleneck. Okay, they will squeeze in, rushing in. They will run faster. But I just want you to know, if you just have PGF and CF, your wind eventually will be parallel to your isobars or those contour lines, upper level. Okay, parallel. So let me clear my drawings. Let me show you the example. So you can see, again, our upper level chart. Okay, this time, let's take a look at it. Let's take a look at those wind. You can see, like I showed you earlier, wind, you see this bar, right? That means the wind go this way. Do you see them? Do you see they are parallel to those bars? Right? They are parallel. They try to follow the direction of your contour lines right here. Right? So that is because they just subject to two forces. One is pressure gradient force. The other one is what? Coriolis force. Okay? So basically at the beginning, your air want to go this way. Okay, they want to be 90 degrees to your isobars or to your contour lines from a high to a low. But Coriolis force want to turn them to the right. So that's why they go this way. Okay, yes, so that is the thing. Okay, so if you read the textbook jargon, meridional and zonal. Okay, meridional means they go north and south, this vertical direction. Okay, zonal means they go roughly east to west, this direction. Just jargon. Okay, just different term. Zonal flow and meridional flow. Meridian actually means your longitude lines. Okay, all right, great. So far so good? Okay, good. Okay, let's go to the next slide. Okay, so very useful thing actually, upper level wind example is your jet stream. Okay, jet stream, especially this so-called polar jet stream, have impact our local weather a lot. Okay, just want to highlight this upper level wind flow, the jet stream. Okay, so you don't have to know every single details about this jet. Okay, later when we study the weather, the severe weather, we will revisit it. Okay, so don't worry at this point, it's just the upper level flow when you hear, oh, jet stream. Okay, but I do have a video on our study guide. Watch that one, you will see how it was produced. Okay. Okay, Rossby waves, the things. Okay, Then let me finish this one. Today we probably cannot finish all the slides because I have 40, okay? So maybe we can continue that on Thursday. If you can, please come in. I will finish my slides, okay? If you can't, let me think a better way because, okay, let's do this. Today, let's finish the 3 forces. And this afternoon, I will make a video to show you the key things on each slide, okay? I will make it available in addition to our class meeting, this one. And you can watch that one. But do let me know on Thursday if you have any questions, okay? All right, okay. So surface wind. Let's take it slow. Sometimes, you know, slow is fast. Slow is fast. Be patient, okay? Enjoy the learning. Okay, on the surface, we have PGF, we have CF, we also have friction, which means your air can never go like this, parallel to your isobars, okay? Because of the friction, your air eventually actually go this way, okay? They cross the isobars. They cannot go parallel because you have this additional friction to balance out everything else, okay? So cross the isobars with certain angle, but that angle is determined by how strong that friction is, how strong your wind is, okay? And which latitude you are at, okay? That angle will vary, but definitely not parallel, okay? All right, so let me change to mouse. Here, clear the drawings. Okay, so let's compare that, okay? Well, here, you can compare that in a real world situation, but let's use a simple example first, okay? Here, you can see upper level here, this elevation, 3,000 meters, okay? Those are the upper level wind. You can see, well, they just try to stay parallel to the isobars, right? Okay, and 0 meter at the ground, sea level, you can see your surface wind, they always try to cross the isobars with certain angle, okay? But always from high pressure to low pressure, okay? I highlight the difference here, okay? Upper level is parallel, lower level is not parallel, okay? And upper level is faster. Why is faster? Can you give me the reason? Why upper level is faster?
Less pressure?
No. Think about 3 forces.
Less friction?
Exactly. High five, Professor Ian. Yes, exactly. You have no friction. You ski, right? You want to ski on the ice. You don't want to ski on our beach, right? Right? On the ice, you have less friction. Upper level, you have less friction. So they always go very, very fast. Okay, so here, let's see. Clear the drawings, mouse. Let's go to the previous slide. Oh. Okay, let's go here. This is a real world example, okay? So you can see, let's go to the surface, for example, okay? Oh.
You're muted.
I accidentally muted myself, sorry.
It's okay.
Let's go to Washington State, or let's go to our local area. Okay, let's go to LA. We are right here. Let's make it larger, larger, larger. Okay, here we go. It's a little bit, you know, busy, but this is LA. Do you see that? Okay, this part of LA. Okay, and you can see our wind. This actually is the station model. Let's use this one. Let's use this on the Channel Island. Okay, you can see this wind. Oh, let me draw. Okay, this wind is from, you know, northwest blowing to our Channel Island. Okay, and the speed, you have two long bars right here. Okay, which means 20, about like 20 miles per hour. Okay, 20 miles per hour. Let's take a look at our upper level at the Channel Island. Okay, so let's go here. Mouse, weather maps. Okay, let's go back to 500 millibar. Okay, let's make it larger. Okay. Let's go to file A. Okay, right here. It's about here, right? Okay. You can see, let's see, make it larger. Yes, this is the faster way. Okay, right here, about here and here, we can estimate it. You can see now you have 3 bars. You have 3 bars here. That is the 30 knots. That is 30 knots. Okay, you have 30 miles, more than 30 miles per hour, the wind closer to our Channel Island right here in this area. Down here to San Diego is weaker, but here you definitely upper level wind is much faster than our local ground level, the wind. Okay, because it's smoother, it's just smoother. Okay, so here, play visit, you will have the real world example here. Okay. Okay. So, okay, upper level, lower level. Let me finish this one. I will let you go. Okay. So here, back to Bert's question. Okay. Well, why we consider upper level? Because they're connected. Okay. So you can see here, if upper level wind, like you have a roller coaster, right? Your air, they want to moving away, okay, from this center, okay, from this center, because the air is a flow, air just like our water, okay? So you can see here, let me annotate it. If the air is diverging out, moving out of this area, okay, you will have less air here, right? It's just like a vacuum where you can replace this low from the ground. So usually you will suck the air up to make up the void because of this divergence upper level. So at the ground, you have less air. You have the rising air, right? Okay, so you end up with a low pressure. And you can see from last module, right? You have the rising air, the water molecules try to condense. You will have the cloud right here. You probably will have a stormy weather, okay? But at the flip side, if the upper level convergence, you have the air moving in, for example, along that trough, okay? You have 2 sides, the air moving into this valley, and you have more and more air. The air cannot go anywhere else. They just need to have to sinking down. Okay, so they will striking on your area. You have a high pressure down to your ground. So when the air is sinking, you never have the cloud because the air cannot condense. You know, the water cannot see the condensation of the water. So you have very sunny weather. It's just like LA. You know, during our summer days, we have very strong high pressure control our area. So that's why we have very dry weather. Okay, and when the air, you know, sinking down, striking on the Earth's surface, they will moving out. You have this divergence, and here you have the convergence. Okay, so you can see in many cases, many situations. Okay, your lower level high low pressure actually is determined by how the upper air flow. Okay, so that is the thing. Okay, here jargon, guys. This so-called hydrostatic equilibrium. Okay, equilibrium means balance. This balance means there's no up and downs. No up and downs in your air column. No, there's no up and downs. They basically just, you know, static air, or the ups and downs, they cancel out each other. Okay, so this is a hydrostatic equilibrium. What does that mean? Okay, actually in many days, our air is hydrostatic equilibrium, especially there's no cloud and there's no upper wind moving upward. Okay, in many situations it's hydrostatic balanced. Okay, but when the upper level air is changing, okay, they're moving faster or they're moving slow, you have that jet stream, you know, coming in, try to, you know, create those situations, divergence or convergence, that will trigger the lower level, the wind, high pressure or low pressure. Okay, yeah. All right, so today, let me just stop here, okay? Let me stop here. Clear the drawings. Okay, today we learn what is air pressure. In which situation, let me go back to the first slide. That's a better way, okay? Okay, let me stop share. Cover this. Let's go to the top, to our outline. Present. And let's share right here. Okay, so today we basically talk about what? This. Air pressure, okay? What is air pressure? What are the factors? Very important, guys. What are the factors influence air pressure? Okay, and how to measure air pressure? Okay, instruments, barometer, different unit. Okay, millimeter mercury. Okay, and surface map and upper level map, how they're defined. Surface map, you draw the line, try to connect different air pressure, or try to connect the same air pressure, but you will see the different lines, they represent different air pressure, right? But upper level chart try to represent to which height you can find certain air pressure, like 500 millibars, right? Okay, 3 forces on wind, pressure gradient force, Coriolis force, friction, okay? Upper level wind just subject to 2 forces, pressure gradient force and Coriolis force. So they can blow parallel to your isobars or contour lines, okay? But surface wind, because of friction, right? Number one, they're slower. Number two, they can never go parallel. They always cross the isobars, okay? And okay, those parallel wind, by the way, we call that geostrophic wind, okay? And you want to know one good example is your jet stream, okay? And vertical air motions, what cause it? Because you don't have this balance. You have the upper level wind, they go diverging or they go converging, they will trigger, you know, the lower level at the surface, high low pressure. They basically will mess up this balance. Okay, they're connected. They're connected. Does that make sense, guys? Okay, so this afternoon, let me end the meeting today. This afternoon, I will make a video about local level. Okay, those are the rest of 4 important concepts. Okay, and on Thursday, if you can, okay, come on in, we can go through the slides together again. Okay, but you're welcome to just watch the video. Okay, all right, so let me stop share. Any further questions before we go?
I was just gonna say thanks for explaining the jargon, and because it can be a lot of information in the different ways
Exactly.
that you're presenting it, but that helps to know.
Thank you. Exactly. I feel the same thing. I'm like, no, our student, you know, we can never understand this if you're just new to this field. Okay, so I want to take it slow. Okay, and then we can learn. The ultimate goal for our class is to learn, right? It's not to just you know, give you points, you know, judge you, evaluate, those type of things. I hate, you know, I hate those things. I want my student to learn, to know something new, because that is the #1 important, and especially during this very difficult time. Okay. Yes. Okay, let me stop share. Okay. Burr, you also have the question?
Yeah, just from the previous videos I was watching, and I was like, it's just a silly question, but I just want to get clarification.
No,
it's
no
like,
silly question.
So we see, as you know, the equator as in like a center for north, south, east, this poles, right?
Mm-hmm.
So about sea level, does it mean like only work with altitude, or do we use sea level for like measure specific you know, pressures depending on that, like a center kind of like is it like a starting point for altitude, like the sea level we consider it?
Yes, yes. Sea level is your starting point when you measure the height, elevation, or we call that altitude. So that's 0. It's just like on your ruler, you know, you have 0 inch, right? From there, you measure certain distance. And from sea level, we measure the height. So for example, here on this slide, let me share this one. So you can see, well, you say location A, they have the elevation 600 meter, right? Let me present it. Can you see that? Okay, so you can see here, this one, okay? So you can see location A, height is 600 meter, measure from where? From the sea level. Okay, so this is how you measure the elevation. Exactly, you got it.
Perfect. Thanks, Professor. And one more thing.
Uh-huh.
So if we not talking about pressure, means it's a vacuum, right? If you don't have a pressure.
Exactly. Exactly. You cannot breathe. In the universe, it's vacuum.
Okay, no pressure means vacuum.
Right, you can say that. You can say that. That's actually creates this phenomenon. Okay, let me clear my drawings. How to go up. Okay, oh, here we go. So this phenomenon, this experiment, this tube in it originally is vacuum, nothing in it. So the pressure is 0 in it, okay? So our air pressure actually can push, can squeeze your mercury in because they have a higher pressure. In fact, they're 13.25 millibar. Inside, you're 0 millibar, right? So that's why they can squeeze the liquid mercury into this tube. Watch this video. it's actually very hard to create this vacuum. You will see how smart they are, okay? Yes. Okay. All right, so any other questions, guys? Are we good? Okay, yes. Are we good? Okay, let me stop recording. Okay, it's so great to see you today, and I hope you learned something.